Welcome back to another video. Here, we will talk about normal confidence intervals on two samples. Now, let's dive in on inference on the difference in means of two normal distributions when their variances are known. We have two populations, and instead of studying them individually, we want to better study them relatively. We want to see how far their means are. Suppose we have a random sample of size n, x1, x2, up to xn, with an unknown population mean, mu of x, and known variance sigma squared of x, and a second independent random sample of size m, y1, y2, up to ym, with an unknown population mean, mu of y, and known variance sigma squared of y. We are interested to make an inference on the means of these two populations. Everything we discussed are summarized here. We have two independent populations represented by x and y, creating two independent random samples, one from each of these populations. And we are assuming the variances of these populations are known. We can assume that, as sample mean is a very good, even the best, point estimator for population mean, the difference in sample means, x bar minus y bar, would be our best point estimator for the difference in population means, mu x minus mu y. We can easily use the linear properties of expectation and variance to calculate the expectation and variance of this point estimator, and use it to build a new standard normal statistic which can help us construct the confidence interval around the difference in population means. The new normal statistic is x bar minus y bar minus mu x minus mu y divided by square root of sigma square of x over n plus sigma square of y over m. We already have a normal statistic and we want to use it to construct a confidence interval with 1 minus alpha % level of confidence around mu of x minus mu of y. To do so, we should define lower and upper bounds so that the probability of mu x minus mu y being within these bounds is 1 minus alpha. To build the confidence interval, we push half alphas to each tail of a standard normal distribution. Given that the area under any probability density function is equal to 1, the area in middle of the PDF should be equal to 1 minus alpha. The corresponding z-values are z of alpha over 2 and z of 1 minus alpha over 2. Taking advantage of symmetry of a standard normal distribution, we know that the z-value of alpha over 2 is the same as the negative value of z of 1 minus alpha over 2. Now, we can claim that the probability of any z random variable being between negative and positive values of z of 1 minus alpha over 2 is equal to 1 minus alpha. To get the bounds around the difference in population means, we use our z statistic in hand, x bar minus y bar minus, the difference in population means, divided by square root of sigma square of x over n plus sigma square of y over m. Next, we multiply all sides with square root of sigma square of x over n plus sigma square of y over m to remove the denominator, subtract x bar minus y bar and multiply all sides by a negative 1. Doing these actions helps us to define the lower and upper bounds around the difference in population means. The two-sided confidence interval starts from x bar minus y bar minus z value of 1 minus alpha over 2 times square root of sigma square of x over n plus sigma square of y over m to x bar minus y bar plus z value of 1 minus alpha over 2 times square root of sigma square of x over n plus sigma square of y over m. Instead of having two-sided confidence intervals, we can also define one-sided ones. This means that there are cases where we want to bound the difference in population means only on one side. The only thing different in our approach is that instead of pushing half alpha in each tail, we would push the whole alpha in a single tail. In the case here, we are pushing all alpha to the right tail. This means the probability of any standard normal random variable being less than z-value of 1 minus alpha is equal to 1 minus alpha, as the area under the curve prior to this z-value is 1 minus alpha. As this equation should work for any standard normal random variable, we can use our normal statistic here. Similar to our steps in developing the two-sided confidence interval, we multiply both sides inside the parentheses with square root of sigma square of x over n plus sigma square of y over m to remove the denominator, subtract x bar minus y bar and multiply both sides by a negative 1. Doing these actions helps us to define a lower bound around the difference in population means. If we are interested to find an upper bound instead, we need to repeat these steps with a minor change in the beginning. We need to push all alpha to the left tail, and we'll have the probability of any random variable z being greater than negative value of z of 1 minus alpha is equal to 1 minus alpha. That is how we can get two one-sided confidence intervals around the difference in population means. One from negative infinity to x bar minus y bar plus z value of 1 minus alpha times square root of sigma square of x over n plus sigma square of y over m. And the second one-sided confidence interval would be from x bar minus y bar minus z value of 1 minus alpha times square root of sigma square of x over n plus sigma square of y over m to positive infinity. Here, we can review all we learned about normal confidence intervals. We know that normal confidence intervals are constructed to help us with inference on population means when the variance is known. We introduced two statistics, both of which follow standard normal distribution. We also discussed how we can construct one-sided or two-sided confidence intervals based on our needs to bound the population mean on one side or both sides. If we look closely, we can see that structure of these confidence intervals are very similar. In case 1, we are interested to study population mean, mu, and used point estimator x bar to construct the confidence interval. Looking closely, we can see that the structure is the point estimator, x bar, plus minus a z-coefficient multiplied by the variance of the said point estimator. In case 2, we wanted to study the difference in the population means, and we used the difference in sample means as our point estimator. Again, the structure of this confidence interval is the point estimator, x bar minus y bar, plus minus a z-coefficient times the variance of the said point estimator. Let's go over an example together. Students, male and female, have participated in a survey regarding their height. Find the 95% confidence interval on the mean difference height of the female and male students, knowing that female and male have variances of 52 and 8.52, respectively. To build the correct confidence interval, we need to identify the parameters of interest. The question is asking to find the 95% confidence interval on the mean difference height and is giving us two samples and is giving us the population variances. Given that we are working with two samples, want to define the confidence interval on difference of population means and the population variances, we can conclude that we should use the normal confidence intervals on the difference of means. To do so, we need to load the confidence interval norm2 function and pass the required arguments. The backend of the said function will calculate the sample means, retrieve z-coefficients, and report the lower and upper bounds of 95% confidence interval as 0.65 and 3.26, respectively. Thank you for listening to this short lecture on normal confidence intervals, one difference in population means with two samples.